This is the final one of the videos where we go through functional groups and lessons. There is a further video on what happens if you add deuterium oxide that follows this. But let's get on with the functional group we're doing today. So we look at the NMR and look for what we can see and also what we can't see. So we've got an N and an O in the molecular formula. So N and an O. So that kind of starts me thinking amine, alcohols, amide, things like that, because an amide has an oxygen and a nitrogen in it. But let's see what we've got. We've got a singlet with a 1 by it. Okay, that could be an amine, that could be an alcohol. We don't really know yet. Okay, and then we've got a CH3 and a CH3. Now, if we look at that, CH3, CH3, and we've got 1 carbon left over. So we've just got 1 carbon left over, and that is it. Okay, and we've got the N and the O to play. So that means both the N and the O must be bonded to the carbon. So I think we've got an amide here. Okay, now if that's an amide, then this is the NH of the amide, because it could be an alcohol or, for example, an NH, but because of what we just said there, we don't think that is an alcohol, we think it's an NH. So let's put that into our table. Okay, so our table with chemical shifts, peak splitting and peak area. We know we've got 3 hydrogen environments, and the singlets all mean that there are no hydrogens on the adjacent carbons. Okay, we can tell from there that the first one, the CH3 is the first one, CH3 again because the relative peak area being 3 and 3. And after our discussion, we think that this might be an NH. Okay. Let's check the molecular formula and check that all works out. Well, we've got CO remaining. So because we have a CO remaining, this again says we've got a CO and an NH, says amide again. So let's put this over to the side and have a look at this potential amide. So we know we've got a CH3 and it's a singlet, and we've got a CO, and we think it's an amide. So let's draw the amide at the centre of what we're doing. So there's your amide. We know we've got a CH3 that is coming off a carbon with no hydrogens on. Well, the carbon with no hydrogens on is right here. So I'm going to put a CH3 here. We also know that we've got a methyl that again is next to a carbon with no hydrogens on, or could be next to the nitrogen because you can't peak split through a nitrogen. So I'm going to put my other CH3 here. Okay, and then we've got our NH. Okay, so this looks like N-Methylethanamide. Okay, but let's go through this and see whether it works out. So we have this hydrogen, this proton, next to a carbon, next to that carbon with no protons on, so therefore it will be a singlet. Okay, that'd be a singlet with a relative peak area of 3. Relative peak area of 3, singlet, good. Okay, we also know that this can't peak split through a nitrogen, so therefore this will be a singlet, again with 3. And we know that this also will be a singlet because all NH peaks are a singlet because you can't peak split through that nitrogen, and that will have a relative peak area of 1. Now that fits with all of this here. But the problem we've got again is we've got our structure, we know what our structure is, okay, but which one is it? Okay, and the problem you've got is when you go on your data sheet, you can see that CO, CH, the CH, CO, and this NH, CH, okay, and you should be looking at your data sheet right now, come out in the same place, 2 to 3. Now also it says on the data sheet that this is only a guide, and this is why. If you look here, 1.8 isn't in between 2 to 3. It's round about 2 to 3, it's a guide. So the data sheet is a guide, rough guide, it doesn't say exactly where these peaks are going to come out. That's why I don't always use the data sheet when I'm trying to teach people how to do this. I try and do it without the data sheet and then confirm with the data sheet if needs be. Okay, so we have to assign both of these an actual CH3. So it has to be this CH3 or this CH3. And the problem with the datasheet is that both of these peaks would come out roughly in the same area. So it doesn't really matter which one you assign to which one, as long as you assign. You can't just leave it as CH3s because they're both CH3s. So I'm going to tell you, if you look here at this CH3, the one by the nitrogen, that is directly connected to an electronegative element. And hopefully as you've gone through this, you see that downfield, more electronegative elements, or the hydrogens connected to the more electronegative elements, move further downfield. And you can see that from your data sheet. So this one will be further downfield, for example, than this, because you have to go through the carbon to get to the oxygen. So that's why I'm going to put the first one at a lower chemical shift, and then I'm going to look at the second one going to a higher chemical shift, and I'm going to assign both of those, and that's how I'm going to assign both of those. And I've put it so that you know whether there is no ambiguity. It is unambiguous. Okay, but I'm pretty sure if it came to it, you could probably just put it down in either for the exam, because they're not going to be too precious about it, because they're both in the same, roughly the same region. Anyway, this is how to determine an amide, and in this case, N-Methylethanamide. In this NMR, we've looked for an amide, and we've seen an amide. If you have a nitrogen and a CO fragment, then you should too be looking for an amide. Now, your nitrogen could be in a secondary amide, or it could be a primary amide. So if we look here, a secondary amide is going to give that short peak with that wider bottom, okay, with a 1. And we had that today with this NH attached to this CO. If it was a primary amide, you would have the same peak but a 2 by it. And again, we've got a primary amide here, which is ethanamide, 2 hydrogens here, and therefore the peak would have a 2 by it. But certainly look out for these amides if you've got the CO and an N in your molecular formula.